I'm Durwood Zaelke, the president and founder of the Institute for Governance and Sustainable Development, also the co-founder of CL, the Center for International Environmental Law, some many years ago, 1989, the founder of the Joint Program on Comparative and International Environmental Law at American University Law School, co-founder of the Program on Governance for Sustainable Development at the Brin School of Environmental Science and Management, the University of California, Santa Barbara. Merely an excuse to go back to one of my favorite beaches in Santa Barbara, but a great place where I still occasionally teach a course on climate justice. I'm the co-author of the leading textbook on international environmental law and policy, the standard text in English, that is, with David Hunter and Jim Salzman. And we just published our 6th edition a few months ago. It's a mere, I have it right here as a matter of fact. I use it to prop up my, my computer. This is one of the great uses for it because it's 1,600 pages.
Oh, wow.
And probably weighs about 7 pounds. So you don't want to carry it around in your suitcase. Anyway, yeah, so I focus on fast mitigation. You know, this is my beat. What can we do to solve the fast 50% of climate change and take out 50% of the rate of warming through principally the non-CO2 climate forcers, but also preserving our sinks. Don't cut your forest down or destroy your wetlands. That's fast mitigation. And then some albedo modification with people like Leslie Fields and her work on the silica beads in the Arctic, hugely important. So, and I have a wonderful group of colleagues at the Institute. Gabrielle Dreyfus, Dr. Gabrielle Dreyfus, our chief climate scientist, and just a terrific scientist and a terrific colleague. I met first when she was at the Department of Energy, and I enjoyed working with her so much under the Obama administration, and was just impressed with her talent that I offered her a job right after Trump came into office, and she accepted. And then she sent me a resume. And it was only then that I discovered she'd gone to Harvard College and had a PhD from Princeton. So I hired her because I knew she was good, but she also happens to have some extraordinary credentials. Your call sign for Skype or something is Ice Princess or something. Did you spend a lot of time actually doing ice cores? I know that's part of your work. And you
Ice
did
Core Princess, yes.
Ice Core Princess, and you did part of your PhD in Paris as well. You happen to live in the same little island here, Ile Saint-Louis. Your mother is French, I know that. And so Gabby has really, really broad range of talents, and has been the lead author of this paper that we just published in the Proceedings of the National Academy of Sciences. It's the 5th paper that IGSD has done over the last 15 years in PNAS. And it is, hard to say this with all my other colleagues, but it's currently the most important one, that's for sure. And the embargo just lifted on Monday, 2 days ago. And so we've been slogging the press with considerable success. A great story out of Reuters, an even better story out of the Guardian, Fiona Harvey's piece. Inside Climate News, Phil McKenna. Gabby appeared on Channel 4 News in London yesterday, did a great interview as the key interview to a great piece done by their lead on-air person, whose name I've forgotten, Alex, I guess. And then we had an embarrassment of riches because we'd committed to a second television interview with Sky News. And then I was told by our media person that we'd given an exclusive to Channel 4. So I had to backpedal and find one of our colleagues from Clean Air Task Force to take over that spot. He did a very credible job, Jonathan Banks as well, on 20 minutes notice. So anyway, it's a really important paper. And I think you guys will know the punchline. You know, methane and the non-CO2 forces are what's going to save our planetary ass. You know, but Gabby has explained this in the most sophisticated way possible, along with Yang Yu, Texas A&M, Ramanathan at Scripps, Drew Schindel at Duke, and myself as co-authors. So, Gabby, over to you.
Yeah, thanks, Durwood. And I don't know if I need any further introduction. Thank you for that. I do want to, I think you had Ewan Nesbitt on a little while ago. He did a great wrap quote on the Reuters piece. So really appreciate that and get the message getting out. And it's not a straightforward message. So with that, no further ado, do you mind if I jump in and do a share screen? Because I got some slides that should help walk through the key findings of this paper and why it's important and relevant to methane action. So the title of the paper is Mitigating Climate Disruption in Time, a self-consistent approach for avoiding both near-term and long-term global warming. So already there are two key concepts in the title, the concept of temperature and the concept of time. And so I'll go into more detail, but really differentiating and disambiguating. When people talk about exceeding threshold temperatures, there's a very important question of when. A lot of the IPCC reports have focused on 2100, which is now less than 80 years from now, but still quite a bit distant, and we have to get there. And so one of the key concepts this paper is talking about is near-term warming, and specifically how the strategies to address near-term warming are complementary and distinct from, in particular, decarbonization. That's the phasing out of fossil fuels that is essential to limiting that longer-term warming. As Durwood said, we have a number of really amazing co-authors, very, very distinguished scientists, Yang Yu from Texas A&M, Drew Schindel, from Duke University, now formerly with NASA, and Ramanathan from Scripps, now also with Cornell. And so the major findings from this paper, I'll jump straight in, are that we're really dealing with two climate crises at the same time, and we need to win against both. We need to survive both. And this has to do with the fact that we are currently warming at a rapid rate, and that we will likely exceed the 1.5 guardrail by the early 2030s. The new UK Met WMO report indicates a 50-50 chance that one of the years in the next 5 years will exceed 1.5, and that the average over the next 5 years could as well. Now, the IPCC takes a little slightly more conservative. They're doing a 20-year climatological average, but they're saying that that could be exceeded by 2030. And the key point when we start thinking about time and the temperature and time, especially when we're thinking about feedbacks and tipping points that are sensitive to the magnitude and duration of warming, is that policies that phase out fossil fuels, that are decarbonization, that are targeting on zeroing out CO2 alone are insufficient. That in isolation, these policies don't provide they don't slow that near-term warming. In fact, they can contribute to a weak near-term warming. And so that they are alone not going to keep us below the 1.5 guardrail and may not even keep us below the 2-degree dangerous threshold. And it's for this reason, when we start thinking about temperature in time, that we need to urgently broaden our approach to climate mitigation. So most of my talk is focused very much on the mitigation side, the emission side, but I'll get to some of the other interventions later. So because that's what the paper was focused on, existing scenarios that are focused on those mitigation strategies. And just to clarify for the climate community that when we have to complement our fossil fuel phase out with targeted measures. These things don't happen by themselves on short-lived climate pollutants, these largely neglected pollutants. Methane is getting more attention, but also hydrofluorocarbons, black carbon soot, and other ozone precursors that are very potent and short-lived, so can have a faster impact on warming. This is the graphical version of that conclusion, where you have on the bottom axis time and the vertical axis temperature above pre-industrial. And you can see that the orange curve, which is a scenario that we constructed using fossil fuel phase out. So it's essentially existing scenarios that have aggressive reductions in fossil fuel use, that those don't, you actually get this acceleration in warming for the next decade compared to the green curve, where the green curve is based on these very aggressive 1.5C compliant scenarios that are in the IPCC reports. And so the point being is only by coupling this decarbonization set of strategies with strategies that target these short-lived climate pollutants can we actually slow warming and even reduce in half the rate of warming by 2050 compared to those policies that target CO2 alone. And again, this just to summarize what we were just seeing in those figures is that by this combined approach, we can reduce the rate of warming in half between 2030 and 2050, which is a decade or two earlier than the CO2 focused strategies alone. And that gives us a fighting chance of keeping that 1.5 guardrail within sight. So now just kind of step back into explaining where those findings come from. We are currently at about 1.1 to 1.2 above pre-industrial. That's the blue line here. And where the 2018 IPCC special report on 1.5, they had done a linear extrapolation, this darker brown line, to project when 1.5 would be exceeded. This paper by two of our co-authors, Yang Ru and Ramanathan with David Victor, said, well, wait a second, it's not linear. There are three things that will likely result in an accelerated warming. One of those is the fact that emissions are increasing, not just of CO2, but we've seen this acceleration in the concentration of methane in the atmosphere, as well as nitrous oxide and other climate pollutants. The second thing is that we're seeing a reduction in reflective aerosols, in particular sulfates. As we turn off coal-fired power plants and diesel engines, these are often sulfur-containing fuels, and they're the largest source of these reflective aerosols. And as those fall out of the atmosphere, they only stay up there for days to weeks, you reveal more of the accumulated warming that's already in our atmosphere that's in store for us. And the third is, of course, we have natural variability in the system and feedbacks, and hence we're looking actually at an increased rate of warming that would lead us to crossing 1.5 in the early 2030s. And the latest IPCC 6th assessment report by the Science Working Group 1 last August, did also say the newest models are saying 2030, early 2030s. IPCC Working Group 2 on the impacts and vulnerability and adaptation has a really busy but useful summary of why this concept of overshoot that blithely has been modeled. The modelers, models are useful tools, and just need to never forget that we don't live in models, and I'll get back to that in a moment. This concept of overshoot, while potentially economically efficient, is potentially a death sentence for a number of unique and threatened species. You can see that already we are in this light red zone, and it's getting towards purple even at 1.5. And then there's this reason for concern number 5, which is these large-scale singular events. Scientists are very descriptive and don't often use terms that mean things to people. So this is described as what we mean when we talk about these irreversible, abrupt tipping points in the system, such as ice sheet disintegration or disruption to the ocean circulation. And you can see that based on this assessment, we are starting to see, we're already in that yellow zone. We have evidence from observations that we are approaching tipping points in one or more systems, and that those risks increase as we get to 1.5 and get worse, even more dangerous as we get to 2 degrees. And as you know well, part of the reason for this increased risk is that we have, and we know from paleoclimate evidence, that there are these feedbacks in our climate system, that there are tipping points. The climate that human civilization has evolved in over the last 6,000 years is really the period over which we've had the agrarian type of civilization that we are dependent on. That's only 6,000 years of a very stable climate. As Durwood was saying, my background is working with ice cores. I'm probably one of the only people you will ever meet who worked in a freezer in Antarctica, and I don't like being cold, but it was for good science. But our poles are these perennial frozen poles. This is a climate state that was very different from the climate state that existed even 3 million, 10 million years ago. And part of the reason that we have these rapid changes in the Arctic, so right now the Arctic is warming on approximately 4 times faster than the global average, is because we have all these feedback mechanisms, one of which is this ice albedo feedback, whereas we lose the reflective ice and uncover darker ocean and land, more of the incoming sunlight is absorbed. And the Arctic is really critical to a number of these other systems that can tip. And this was a paper that came out that started to look at the relationships and how you can get this cascade of tipping points. And the problem that is that we don't have good quantification of these processes. And so none of the models actually account for the interactions between these types of tipping points, which is why they're not well reflected in the current modeling analyses. And that's something that actually, I believe the Swiss government is proposing a special report to the IPCC on this, but it will require actually quantifying and better understanding these processes and how they relate. But an example here, for example, is this warming of the Arctic that can lead, that we know that Greenland could be committed to melting at around 1.6 degrees above pre-industrial. We already have lost about half of the summer sea ice cover. And we're seeing that we could be within a decade in September have no more summer sea ice, which again, with that ice albedo feedback is equivalent to adding about 1,000 gigatons of CO2 in terms of the warming effect. And as Greenland melts, it adds fresh water to the North Atlantic, which is where deep water is formed. And so and we're already seeing evidence of this slowing ocean circulation. And then this has effects as that circulation changes. And we're already seeing effects on the jet stream, on forests and other ecosystems. I know that I don't want to dismiss, of course, the additional radiative feedback as we lose land snow cover, which also increases this albedo feedback. And as you know well, there's a lot of carbon, organic carbon and methane, hydrates and other organic carbon that's been frozen in the permafrost and in the seabeds that could be destabilized through these processes. So speaking about living in models, let's start talking about why it is that strategies that focus on phasing out fossil fuels, on decarbonization alone are insufficient to slow warming in the critical next 10, 20 years. So this curve, the blue curve is I want folks to focus on first. It's actually a piece of good news. The models show that if we were able to turn off all CO2 sources instantly, we would basically be relatively flat in terms of warming. And this is good news because the oceans take up about 90% of the heat, and there is this concern about how quickly the oceans will re-release that heat to the atmosphere. That's essentially warming that's baked into the system. And as you can see from this quote, it's not, it wouldn't be too bad in terms of the prospects. However, more importantly is the red line. Policies and mitigation strategies generally don't act on a pollutant. We don't police every molecule of CO2. What we do is have policies that act on sources. And the primary source of CO2 is burning of fossil fuels. And if you take a coal plant, for example, when you burn coal, there are additional pollutants that are released with the CO2. And if it's a sulfur containing coal, and if you don't have scrubbers on, you get these reflective aerosols that are masking about 0.5 degrees of warming right now. And so if you turn off those coal plants, you actually unmask that warming as those sulfates fall out, and you get that jump in that red curve. So what we're talking about is the purple curve, which is how do we do the turning off the coal plants and address these non-CO2 climate forcers, methane, hydrofluorocarbons, black carbon, and other ozone precursors. How do we turn those down so that we can actually get this as much avoided warming in as short a time as possible to compensate for that unmasking? And so this is another way of looking at this issue of the masking from sulfate aerosols that is from the August IPCC report last year, Working Group 1, where for the first time, they converted this concept of radiative forcing into the temperature contribution. And so you can see from the figure on the right that as far as the historic emissions are concerned, carbon dioxide emissions from all sources is adding about 0.8 degrees of warming compared to about 0.5 from methane. And I want to be clear here, this is considering all of the direct and indirect forcing from methane. There are studies that make methane look smaller if you're only taking the concentration of methane in the atmosphere. But because we know methane is short-lived, it breaks down relatively quickly. But what does it break down to, and how does it react to the atmosphere? It does produce CO2, but it also is a major source of ozone, which is a radiative gas that is also, and so that's added in here. And it also has an effect on water vapor in the stratosphere that also increases its impact. But you also have these cooling aerosols, these cooling human influences. In particular, the biggest is sulfur dioxide, which is a precursor for these reflective sulfate aerosols that are almost entirely co-emitted by the same sources that are your CO2. And so what our paper does is build on this study that came out in 2019 by Drew Shindell and I think it's Chris Smith. And it was reading this study, and in particular, note when you read a study, read the methods, because it was in the smaller print methods at the end of the paper that the authors acknowledged that the only reason that these 1.5 consistent scenarios showed any avoided warming in the next 20 years is because they assumed that we were also reducing the non-fossil fuel, so methane from agriculture, and landfills, but also phasing out fossil fuels doesn't address leaks from abandoned mines and abandoned wellheads. Those you actually have to go in and remediate. And so this figure from their study shows that when you put the CO2 and its co-emitted sulfate aerosol reduction together with that fossil fuel phase out, these are different colors for the different modeling runs, different actually models that they assessed, you actually get this weak near-term warming because of the net effect of those sulfates falling out. And so by 2050, with this very aggressive fossil fuel phase out, it's not really until 2050 that you get about 0.1 in avoided warming, which is still important, but you have this weak near-term warming when you look at the net effect of the fossil fuel phase out. In contrast, if you focus on methane and these other short-lived climate pollutants, this blue line here is from the global methane assessment. If you do a 45% reduction in methane by 2050 relative to the 2030 baseline, you actually could avoid up to 0.3 net. I'm gonna get back to that net. So methane sources generally aren't the same sources as for the sulfate aerosols. And I do want to acknowledge that there's a little bit of double counting here. About a third of this methane signal you get from some of the fossil fuel phase out, because methane is a fossil fuel when it comes from natural gas sources. And again, because you have this Arctic amplification, that reduction in methane, while it's 0.3 globally, is actually closer to half a degree avoided warming in the Arctic. So don't take our word for it. IPCC studies also looking at the benefits of combining the mitigation with methane and black carbon to offset this near-term warming. A 2011 study from the Integrated Assessment of the UN Environment Program and World Meteorological Organization also looked at strategies focusing on targeting methane and black carbon and found that they could slow the rate of warming in the Arctic by 2/3. Again, the Arctic is extremely sensitive to black carbon emissions and cut the global rate of warming in half. And so, really, what our study, the real addition of our study is to look specifically at the strategies focused on decarbonization, fossil fuel phase out, and compare what that gets you to these combined strategies. And so a really, really key point here, because some people go, well, if shutting out coal plants causes short-term, near-term warming, maybe we should slow that down. And the answer is absolutely not. We need to do both. While the faster, deeper cuts to sources of CO2 have this limited effect on near-term warming because of aerosol unmasking and the slow carbon cycle, they are absolutely critical, because every kilogram of CO2 we put in the atmosphere stays there for centuries. We got to stop them now if we also want to win that longer-term climate crisis. But we have to cut methane to do and these other short-lived climate pollutants in the near term. So these are it's really important. These are not interchangeable. This idea of global warming potential, regardless of timeline, implies that we can trade these things off, but they're actually two different strategies to address two different climate crises. And so we need to do both. And the way that we express this, you've almost certainly heard Durwood say this is his framing, that we are running 3 races at the same time. The first is the sprint this decade to slow warming by cutting these short-lived climate pollutants, in particular methane. At the same time as we're doing the sprint, we're running this marathon to decarbonize, to get to 0 CO2 emissions. And at the same time as we're doing that, we're running an ultra marathon to develop the carbon capture and methane removal technologies and prepare for climate interventions and geoengineering type interventions. And so we really need to be running 3 races to be able to stay in the race long enough to decarbonize and stay key and to have a livable planet. So I think that's the most. I did have a few more slides. We can talk more about methane removal. I think you know more than I do about these things. But one of the things that I've been following very closely is the work that RPE is doing and on some of those activities. So with that, I will stop sharing and open it up in case there are any questions.